Swayamprabha. Digital India. Educated India.
So, good morning all of you. So, today we will look at in fact continuation of the last class, which was extending Graetz solution. The Graetz solution was originally proposed by Graetz for slug flow profile, and it looks at the thermally developing region or the thermal entry region, wherein you are hydrodynamically fully developed and you are looking at only the entrance region where the thermal boundary layer is developing. For such kind of that is what we call as region 2. So, Graetz assumed a slug flow, so where anyway the slug flow does not vary and it is uniform everywhere, and he had developed a solution for constant wall temperature, which we had seen earlier. So, there the eigen functions were what were the eigen functions essentially in the original Graetz problem? So, the eigen value problem there was actually a Bessel equation, right. So, now the same problem can be extended to a case which is more realistic, that is for a parabolic velocity profile. Okay, this extension was done by a group of people, Sellars et al, Sellars Tribus, and I have posted that in the Moodle. You can just have a look. Originally in 1954 how they did the extension to the Graetz problem. Of course nowadays the solution is more by numerical methods. They tried to do a approximate technique where they did something for R close to the wall, the R which is somewhere in the middle and R which is far away from the wall, and they patched up all the solutions together. So, what we are doing nowadays is directly go for a numerical solution to the eigenvalue problem. So, the easier way to start is to introduce these non-dimensional variables. For temperature, as usual we define theta as T minus T wall by Ti minus T wall. Since this is a constant wall temperature boundary condition and your inlet temperature is also assumed constant, so this is an appropriate definition for theta. Once you have a constant wall flux boundary condition, then you cannot define theta this way, okay, because when you take the differential with respect to x, your wall temperature will not be a constant and therefore they will not cancel out on both the sides. And this is the non-dimensional radial coordinate, and your non-dimensional axial coordinate can be non-dimensionalized in this manner, which is somewhat similar to an inverse of the Graetz number. Your Graetz number, 1 by Graetz number is actually x by d by Peclet number, okay. So, this is somewhat similar, exactly. Now we are not using x by d here but x by r naught. So, when we substitute into the energy equation, okay, the energy equation for thermally developing flow is this, and if it had been fully developed, your d theta by dx would have been 0, but in this case your flow is still developing, and therefore if you substitute, you get a partial differential equation in terms of theta, which is a function of both the axial coordinate zeta and your non-dimensional radial coordinate eta, and the boundary conditions are at the entry region, that is at zeta equal to 0, so your t equal to ti, so therefore your theta will be 1, and at the location r equal to r naught, that is at the wall, okay. So, your coordinate system that you are looking is something like this. This is your r and this is your x, okay. So, this is your r naught. So, at r equal to r naught, that is your eta equal to 1, that is where your theta equal to 0, where your t is equal to t wall. So, this is where you apply constant wall temperature. And at eta equal to 0, that is at r equal to 0 center line, there is a symmetry in the profile. So, therefore, your gradient at the center line should be 0. So now once you assume that you can use separation of variables to solve this, we introduce theta and we break up the solution as a product of two independent solutions. One is a function of only eta, the other is a function of zeta. So we introduce x as a function of zeta and r as a function of eta, and then substitute into the PDE, and then we get we reduce the PDE to two ordinary differential equations through the eigenvalue lambda square. Okay, and the eigenvalue problem here is basically the one with homogeneous boundary conditions, which is basically in the eta direction. And if you compare this to the Bessel equation, you can find that this last term here is not same. So therefore this is not a Bessel equation. If you look at these first two terms, they appear similar, but the third term is not the same, as it is a function of you have eta. If you multiply by eta square, you will have eta square into 1 minus eta square. That comes different from the Bessel equation. And these kind of general eigenvalue problems are called Sturm-Liouville eigenvalue problems. Okay, so any kind of an eigenvalue problem, whether this is a Bessel equation or a basic ODE, can be represented as a Sturm-Liouville eigenvalue problem. So the Sturm-Liouville eigenvalue problem can be cast into a differential equation like this. Of course you can express this also in this particular form, and the Sturm-Liouville problems have a particular property that when you integrate your eigen function, you multiply your eigen function and you multiply it with the weighing function. The weighing function is this, which appears on the right hand side. So this is the particular property. This is your Kronecker delta. So if m equal to n, then this will be equal to 1, otherwise it will be 0. Okay, so now if you compare your eigenvalue problem to the Sturm-Liouville problem, okay, so you can write your eigenvalue problem into the Sturm-Liouville form. So that will come out as minus d by d eta into eta dr by d eta plus the term corresponding to q of x is 0 here, and this term can go to the right hand side, and that can be expressed as lambda square into 1 minus eta square into eta into r. So I am multiplying throughout by eta, and the first two terms I can combine and write it in this particular format. Okay, now the format is the same as the Sturm-Liouville format. You can compare the coefficients. Your p of x is nothing but eta, q of x is 0, and your weighing function is 1 minus eta square into eta. So this is your weighing function as a function of eta. Okay, so this can be written as 0 to 1. So this is strictly speaking a to b. Okay, in your case your eta goes from 0 to 1, that's why I have just used 0 to 1 there. So this is 0 to 1, and this will be r n of eta into r m of eta into weighing function here, which is eta into 1 minus eta square d eta is equal to delta mn times 1 by 2 lambda, because here your lambda square is your lambda. So this is square root of lambda square, which is lambda n into dr n by d lambda n into dr n by d eta at eta equal to 1. Okay, so this is how the corresponding property of Sturm-Liouville comes out to be in this case. And if you want to write the final solution for theta, which is basically x into r, so you know the eigen functions. Now in this particular case, this is an ODE, and to get the eigen function you have no other option but to solve it numerically. Okay, you can once again go back to your shooting method. You can reduce it to two first order ODEs, and then here guess the value of lambda, because you don't know the value of lambda. Unless you know the value of lambda, you cannot find out the eigenfunction. So guess the value of lambda, and once again you have to satisfy the other boundary condition, and that's iteratively found out, and that is the suitable value of lambda. So like this, for the given value of lambda you have a particular value of eigenfunction. So for each value of lambda you have to find the eigenfunctions, and finally the solution will be a superposition of all these eigenfunctions. Okay, so that can be written as a constant times the eigenfunction into the other solution for x. The other solution for x as a function of zeta, that is a very straightforward ODE which can be directly integrated, and that will be in terms of constant times e power minus lambda square zeta. Okay, so this is your final solution for theta. Having determined your eigenfunctions and your eigenvalues, you can therefore plug in into this expression and find the variation of the temperature. I will just give you a representation of how the eigenfunctions look if you solve for them, and if you plot the first three eigenfunctions Rn, 0, it varies between negative -1 to 1, 0, 0.5, so this is your R0, R1 and R2. This is a representation of so these R0, R1, R2. So here you have plotted with respect to eta. Here, okay. So this is the eigenfunction corresponding to n equal to 0. That is for lambda 0. Okay, and this is the eigenfunction corresponding to lambda 1. So for different each eigenvalue, for eigenvalue lambda 0, lambda 1, lambda 2, you substitute into the ODE and you can get the corresponding eigenfunction variation with respect to eta. So these are the first three eigenfunctions. So these are the most important ones. There are other higher order eigenfunctions, but their contribution will be relatively smaller. So when you sum them, you take only the first 3 or 4 important eigenfunctions into account. Okay. So now the thing is, this is the solution, but still we have to find the constant Cn. Okay. So for this we have to apply the initial condition, that is at zeta equal to 0, and we make use of the property of the Sturm-Liouville. When you integrate with the weighing function, so this is basically, since this is an orthogonal, all Sturm-Liouville problems all are orthogonal. So this is a property which satisfies the orthogonal condition. So this is an orthogonality condition of Sturm-Liouville system of problems, and we will make use of this in calculating the constant. So let me call this as equation number 1, and I am going to multiply both sides by Rm and integrate. So for first, before doing that, I will apply the condition at zeta equal to 0, which is equal to 1. Therefore 1 equal to summation n equal to 0 to infinity Cn, you have Rn of eta into e power minus lambda n square 0, that is 1. So I can now multiply both sides by Rm of eta and the weighing function. Okay, so the weighing function is here eta into 1 minus eta square d eta, and integrate from 0 to 1. So this is also the same. I have Rm eta into eta into 1 minus eta square d eta. Okay, so multiply by this Rm eta into the weighing function and integrate both sides. So now I make use of my orthogonality property. So therefore only for m equal to n this will be non-zero. Okay, so this will turn out to be 0 to 1 Rn of eta into 1 minus eta square d eta. On this side you can sum only if m equal to n, so therefore this will be 0 to 1 and the constant can come out. Okay, so this will be Rn square of eta, because if m equal to n then only this will be 1, so this will be Rn square eta into 1 minus eta square d eta. Okay, so therefore my constant Cn will be 0 to 1 Rn eta into 1 minus eta square d eta divided by 0 to 1 integral Rn square eta into so now I have to evaluate these integrals. How do I do that? For example, the integral in the denominator, how do I calculate integral 0 to 1 Rn square eta into 1 minus eta square d eta?
Using the last one.
Yes, so that will be 1 by 2 lambda n into this particular thing, right? So I already know from the property of Sturm-Liouville system of equations that the denominator 0 to 1 Rn square into eta into 1 minus eta square d eta should be equal to 1 by 2 lambda n into dr n by d lambda n into dr n by d eta at eta equal to 1. Okay, so this is what I get from integrating the denominator. And how about the numerator? How about the numerator? You have a very nice clue. You have basically the eigenvalue problem here. From this, if you integrate both the sides, okay, so if you integrate this, that is basically you have already r into eta into 1 minus eta square d eta, and this will be therefore on this side minus 1 by lambda square into you have eta into dr by d eta, and you are integrating between 0 and 1. So at 0 eta will be 0, so therefore this should be at eta equal to 1, this will be 1, right. So this comes from the eigenvalue problem itself. So I can just integrate and I can find out the value of this. Okay, so therefore now I can write my constant Cn. So if I substitute for this integral and this integral, what will be the constant? Minus 2 by lambda n, and so this will be dr by d eta at eta equal to 1, and denominator dr by d eta, these two will cancel off, so you have only this in the denominator. So you have into 1 by drn by d lambda n corresponding to eta equal to 1. Correct? Okay, so this and this cancels off, you have minus 2 by lambda n and this in the denominator. So now for calculating this constant c as a function of n, this is a function of n. So for different values of eigenvalue lambda 0, lambda 1, lambda 2, I need to know what is the derivative of the eigenfunction with respect to lambda, okay, corresponding to eta equal to 1. So therefore now for different values of lambda, for eta equal to 1 I should know what is the value of the eigenfunction, and then I should fit some approximate curve and calculate the slope, okay. So that basically corresponding to eta equal to 1, from there I can calculate my constant c, okay. So I can finally substitute for c into my equation number 1 for the solution. So therefore the solution for theta can be written as minus 2, this can be taken out and I have summation n equal to 0 to infinity, and for Cn, so the other, these are all functions of n, so I have to just keep it inside the summation. I have e power minus lambda n square zeta into Rn of eta divided by lambda n into dr n by d lambda n at eta equal to 1. Okay, so I have simply substituted for c of n from what I have obtained here. Alright. So finally, once I know my eigenfunctions, my eigenvalues and this derivative, I can now finally find the solution for theta. So this is my final solution. So I will go further and I will calculate the expression for the Nusselt number, the local Nusselt number. So therefore now I will define my local heat transfer coefficient as k dt by dr at r equal to r naught divided by T wall minus T mean. This is my definition of local H, and from substituting the temperatures in terms of theta and everything in terms of non-dimensional radial coordinates eta, okay. So this will be, if you substitute for T in terms of theta, you remember that theta is T minus Ti by, T minus T wall by Ti minus T wall. Okay, so this will be Ti minus T wall into d theta by dr at r equal to r naught divided by T wall minus Tm. Okay. Now I can define a mean temperature, non-dimensional mean temperature, which is theta m as Tm minus T wall by Ti minus T wall. So here T is a function of both r and x, here T mean will be a function of only x. Okay, so I can define a non-dimensional mean temperature, and you see that T wall minus Tm by Ti minus T wall is nothing but minus theta m. Okay, so I can write this as minus k d theta by dr at r equal to r naught by theta m. What I can also do is replace r in terms of eta, so therefore this will be eta into r naught and this will be at eta equal to 1, because your eta is r by r naught, so I can replace directly with respect to eta. So all I need to know is my mean temperature theta m and also the non-dimensional gradient of temperature at the wall. So once these two are calculated, I can find the expression for Hx. So from the equation for theta, let me call this as equation number 2. Now I can go on and calculate the expression for first theta m. So therefore I can write my theta m as follows. So how do I define my bulk mean temperature? According to the basic definition, I take my non-dimensional temperature, multiply it by the velocity and integrate across the cross sectional area. So that is 2 pi into r dr. Okay, so this is from 0 to r naught. So this I divide it again by the mass flow rate. So that is 2 pi integral 0 to r naught into u of r into r dr. Okay, this and this cancels. Now I define my bulk mean velocity or mean velocity as once again 1 by, so this is 0 to r naught u of r into r dr. So this will be 2, this will be 2 by r naught square, correct. Okay, so I can now substitute for this right here in terms of the mean velocity. So this is basically integral 0 to r naught theta into u of r into r dr divided by, this will be r naught square into um by 2 . Okay, so since is only a function of x, I can take this inside the integral and I can write this as u by into r dr. So I can now convert this completely in terms of non-dimensional coordinates. Okay, so this will be 2 0 to 1 theta into u by into eta into d eta, because I have r by r naught here, dr by r naught. Okay, so this will be my expression for theta m as a function of non-dimensional theta and u by Okay, so I can now substitute. I already have my expression for u by What is the expression for u by That is from the fully developed parabolic velocity profile, right? That is twice 1 minus eta square in terms of the non-dimensional coordinate. Okay, so I can substitute for theta coming from equation 2 and the velocity profile from this into theta m. So this will become minus 2 summation of n equal to 0 to infinity e power minus lambda n square eta divided by lambda n into drn by d lambda n corresponding to eta equal to 1 into 0 to 1. Then I have so 2 into 2 4, okay, into eta into 1 minus eta square into r, which is also a function of eta, okay, rn of eta into d eta. I'll just erase . Okay, so I am just substituting for theta and u by into this, and I am grouping all the terms which are function of eta, and that I am integrating from 0 to 1. So that is basically 4 times eta into 1 minus eta square into r into d eta, right. So this eta into 1 minus eta square Rn eta d eta. What is this value? So we have already seen that this is nothing but 1 by lambda n square into dr by d lambda at eta equal to 1. Okay. So we will just substitute that, and my theta m now becomes so 4 into 2 becomes 8 here. This is a minus sign here, okay, just take note of it. So minus and minus become plus here, so 8 into summation n equal to 0 to infinity into so that is a dr by d lambda n at eta equal to 1. No, this should be with respect to eta, sorry, therefore this comes out with respect to eta, please correct it. Okay, so this is drn by d eta here. Okay, so this is one of the terms multiplied by e power minus lambda n square into zeta and divided by, you have a lambda n square here and there is a lambda n here, so this becomes lambda n cube into, already you have a term drn by d lambda n, so this becomes drn by d lambda n corresponding to eta equal to 1. Okay, so this is your expression for theta m. So now you have a closed form expression for theta m as a function of the eigenvalue and the derivative of eigenfunction, both derivative as with respect to eta as well as with respect to lambda. Okay, so now we need to still find d theta by d eta with respect to eta equal to 1. What is this value? Directly you can differentiate, that is minus 2 summation n equal to 0 to infinity e power minus lambda n square zeta into, this will be your dr n by d eta at eta equal to 1 divided by lambda n into drn by d lambda n at eta equal to 1. Okay, so therefore we will substitute for theta m and d theta by d eta so therefore if I substitute, I can so I can also write my, so I have my expression for hx as minus k by r naught. I can directly get an expression for nu which is defined as h into r naught by k. So it should be actually defined with respect to d, therefore I will write this as h into d naught, and so this will be d naught by 2, therefore this will be minus 2 into d theta by d eta at eta equal to 1 divided by theta m. Okay, so I can substitute for d theta by d eta and my theta m, so that gives my nux as summation n equal to 0 to infinity a n e power minus lambda n square zeta divided by twice n equal to 0 to infinity a n by lambda n square e power minus lambda n square zeta, where a n is nothing but drn by d eta at eta equal to 1 divided by lambda n into drn by okay. So I will give you a couple of minutes, you can substitute and check for yourself. It is just straightforward. I am just grouping this entire term dr by d eta divided by lambda into dr by d lambda. This has a constant which is a function of n, okay. So I call this as an, okay. So this will be nothing but therefore an into summation of n equal to 0 to infinity power minus lambda n square, that is the numerator, divided by the theta m also has the same term. So in addition I have lambda n cube here, so therefore this will be an by lambda n square into this, okay. The numerator has basically 2 into 2 4, denominator has 8, therefore there is 1 by 2 there, okay. I hope all of you are clear. I am going pretty slow here. So therefore this is your final expression. Now to calculate my Nusselt number, here I need to basically know numerically the values of all the slopes of eigenfunction with respect to eta as well as with respect to lambda, and also the eigenvalues. So from there I can calculate my Nusselt number once I know the location, axial location where I need to. So my Nusselt number is now only a function of my axial location, non-dimensional axial location. So what Sellars did, if you look at that particular paper which I posted, so he did it numerically and he has predetermined the values of all these constants and tabulated them. So I am just going to give only the final values tabulated by Sellars. Okay, so you can also see the for the value of corresponding to n, lambda n, the value of Cn and An. Okay, so Cn is required where? In your solution for theta. Okay, so that he also everything has been computed numerically. So for n equal to 0, the most important eigenvalue, that is your 2.7043, the value of Cn is 1.466, 0.748, and similarly for 1, 2, 3, I will also give the fourth value, this is 6.6790, 10.67, 14.67 and 18.66, minus 0.802, 0.587, minus 0.474 plus 0.404, 0.544, so 0.462 and 0.38. So the most important, the first 5 eigenvalues, the corresponding constant Cn and An, they were all numerically calculated and tabulated by Sellars et al. 1954. So therefore you can just directly use these values, you do not have to sum them to so many terms, you can just sum them to the first 4 or 5 terms. Okay, so you can directly substitute the corresponding value of lambda A, and in the solution for temperature the value of C, then you can get an expression directly in terms of zeta. Okay, so which is basically your non-dimensional axial coordinate. So for different values of zeta you can actually plot and see how the Nusselt number varies right from the location where your thermal entry length starts. Okay. Now for the limiting case, if you look at a very far away distance axially, so that is for large values of lambda. For lambda very large, you can see that this is an exponentially decaying function. Okay. So except the smallest value of lambda, if you go for larger values of lambda, that is corresponding to n equal to 1, 2, 3, 4, so these are large values and it is already an exponentially decaying function, so they will be very small. Okay. So only the first term corresponding to n equal to 0 will be important when you look at large values of zeta. So for that, this will be reducing to your a naught into so basically you have e power minus lambda naught square into something which is very large, okay, divided by 2 times you have a naught by lambda naught square into e power minus lambda naught square zeta, right. I am retaining only the first term and neglecting all the higher terms, so these cancel out and this will become, so your Nusselt number corresponding to large values of zeta will be nothing but 2 lambda naught square divided by 2. So if you substitute the value of lambda 0 corresponding to n equal to 0, so what will be the value of nu? So that is basically 2.7 the whole square divided by 2. Any of you, anyone who is having a calculator can quickly check that. .6566. So anybody remembers the significance of this number? This is for the case where we started fully developed flows. In the fully developed, both thermally and hydrodynamically fully developed region 3 and constant wall temperature boundary condition. So this was the Nusselt number. Okay. So now that we are getting as a asymptotic solution to the thermally developing case for large values of zeta, the same value. So this is your fully developed okay. So that comes out naturally as an asymptotic solution. Now to wrap up this particular case, as you can see the Sturm Liouville problems, any general Sturm Liouville problems, you cannot find a direct closed form solution, you have to do a numerical solution, and therefore sometimes it is difficult to do so. So once the numerical values are calculated and tabulated, there was a person called Hausen who actually fitted the empirical curves to this numerical solution for different values of n. He took and then he substituted them there, and then he fitted set of empirical curves to the numerical solution, and then he directly proposed an empirical correlation which is independent of all these constants and the eigenvalues. Okay. So that is a very famous correlation. So that goes as nu is equal to 3.66 plus 0.0668 into Graetz number divided by 1 plus 0.04 Graetz number to the power 2/3. Okay, where your Graetz number is defined as 1 over or you can say 1 by Graetz number is basically x by d by Peckley number. Okay. So this is a very simpler correlation, you just substitute the axial location non-dimensional form as a Graetz number into this expression and you directly get your local Nusselt number. Okay. You do not have to find out eigenvalues a corresponding constant corresponding to n equal to 0, 1, 2, 3 for this. Okay, this is an empirical correlation which fits very well with the exact solution. Okay, so you can see for the limiting case where your x by d goes to very large values, your 1 by Graetz number is basically, see here your Graetz number becomes very small for large values of x by d. So then this particular term here disappears and it will lead to the limiting case of 3.66, which is the Nusselt number for fully developed flow. Okay, so if you want to just plot the axial variation of the local Nusselt number with respect to 1 over Graetz number. So you will find that this is for the constant heat flux case. Anybody remember what is the asymptotic solution? 4.3 4.3 roughly. This is for the constant heat flux, and this dotted line here is for constant wall temperature, and the asymptotic case leads to the value of 3.6. Okay, so if you plot the local variation, once you have the first 5 dominant terms, you plot it as a function of 1 over Graetz number, and you will find that exponentially it is a decaying function. Okay, and also you can plot both the constant wall flux boundary condition case, constant wall temperature boundary condition case. The constant wall flux case has a slightly higher Nusselt number, and asymptotically that will reach to a value of 4.3, and constant wall temperature case reaches to 3.6. Okay, so this is to give an idea about the thermally developing region. Now as I said, how do we get the constant heat flux case? Okay, so that's a slightly different problem. Okay, the problems that we have solved in the class corresponding to constant wall temperature boundary condition, okay, and parabolic velocity distribution. This was an extension which was proposed by Sellars, extension of the Graetz problem. Now the other extension is for a non-uniform wall temperature, that is for a case where you can have an axial variation of wall temperature which is a linear variation, or you can also have a constant heat flux boundary condition. So these were proposed also by Sellars, and I have uploaded a document on the Moodle which gives the extended solution for the case of a plug flow. The velocity profile is plug flow, but the boundary condition is a constant wall flux boundary condition. Okay, so there I will probably in the tomorrow's class give you hints how to approach that problem. There the boundary condition is non-homogeneous because you have a defined heat flux. So the thing is, how do we homogenize that boundary condition for getting an eigenvalue problem? So that is the key. Once you know how to do that, after that the rest of the things are straightforward. So to get an idea, you can just look into the Moodle where I have posted for the case of parallel plates. Okay, that's a much simpler case to deal with. It's a Cartesian coordinate system, and taken case of plug flow and constant wall flux condition. Okay, so I'll give you I'll just describe the procedure briefly, and you can go over the document and you can do the same thing for the case of circular tube also. Okay, so with that the developing case will be over, the thermally developing case or the thermal entry length cases will be done, and finally we look at the case of simultaneous entry length problems. So those problems we cannot do analytical solutions because you cannot neglect any terms, strictly speaking. Okay, we have to go for a full numerical solution to the Navier-Stokes equations. There have been some solutions where some approximations have been made, but still they were involving a numerical solution. So I will just give you the empirical correlations coming out of those solutions, and I think tomorrow we should be able to complete this part. And the last two classes on Thursday and on Saturday, we look at the approximate solution to the internal flow problems. So how do we use the integral method here? Okay.